Okay, guys, so let's get started. I think this is working again. Let's see how long it's going to last. All right. So let's see, this is for ES 305. Today is February 2018. And this will be lecture 11 and the page number 64. Okay, so basically you have an exam on Thursday, no? Okay, so before we go maybe into the homework, let's see what you will have on the exam. So my guess initially, I will post probably today before leaving a sample exam, if not today, tomorrow, okay? But otherwise, right now what I have in mind is, what is it? What have we covered so far? I mean, the first problems could be like the ones we did, remember, for the efficiency of a power cycle or refrigeration cycle, the one that was the power plant. If you know the efficiency, what is going to be the cost of running the power plant or a fridge or whatever, no? Okay, I'm guessing something like that. Then looks like I'm going to have to give you also a problem about heat transfer, some type of conduction, radiation, or convection. Yeah, and then one problem about using the tables, no? Those fun ones. Okay, so I think I think you're gonna have something like that. Okay, well, about one about each chapter or each one of the three topics we have really covered in class. Okay, remember, for me the exams are not to trick you or anything, it's just to test that you know the knowledge we are covering, no? Okay, so I'm gonna try to do is to find three problems that basically show if you know the material we have covered so far. Okay, yes?
For the problem with the table, are you requiring us to add our own tables, or will that be provided?
No, you are required to have your own tables.
Sorry, you said you were going to let us know like which ones are the most important ones to have.
Yes, so let's do that right now if you want. So let me then try to go over here. I mean, there are tables that you don't really need. So if you want, let me write it down. So ES305. If we go to the same PDF that I gave you, so basically I will say you need from table A1 and A1E, okay, whatever it is. So you need from A1 saturated, okay, so let me write it down, and then if I need to modify, I think you need from tables A1 to initially to A18 for sure. Okay, now let me see what are the other ones. And the same one for English units or SI units, okay? So in both units, so we say A18, 14. Okay, so this is A19E. I don't think you need this one. you might need this one, so 820. That doesn't mean for this exam, okay? I'm just thinking about the rest of the semester. So 820. This one, you're not gonna need it. A22. That one you might need it. What is this? I don't think you're gonna need this one, but it's just one extra. 823. You don't need this one. And you don't really need this one either, but again, you might need it for a problem. You don't need this one for sure. Yeah, you don't need any one of those figures. You don't need them, okay? None of that stuff we're going to be using. Okay, so let's see. I will say both in for SI and English units, I will say these tables. So from A1 to A20, then, sorry, from A1 to A18 plus A20, A22, A23 plus A25 for SI and English units. Okay, if you don't want to come with a very thick stack, if you print both sides of the pages, okay, you ended up with not that many pages. But it's up to you, okay? If you want to have all in one face so you can just, don't have to go to the back, you are more than welcome.
We can use the copies of pure substances sheets that are on Canvas too?
You can use you can also bring the page for the pure substances that shows you the two shape of the figures as well as the equation to find when it's a mixture. And I think you also, you can use as well, but that one I will bring it all the time, the one for the units. Okay? Yes?
And just clarifying, apparently in my notes there's a few equations that we can add to that sheet, right?
To that equation, probably you can add if you want at the back, because I think you will know them, but what is the general form of the equation for, let's say, conduction, convection, radiation, and I think you should also add what is the value of the constant for radiation, the Stefan's Boltzmann constant, okay? That one you can add it as well. Basically, I don't mind you putting equations, okay? You can ask me, can we put that equation? I don't mind giving you a question. What I want to see is any procedure or any, problem resolved with the magic equation at the end, no? Okay? Okay, I'm not testing your memory. If you need one equation during the exam, you ask me, okay? I'll give it to you. All right? I'm not testing you on that. Or a constant, okay? Don't get stuck because you don't know a constant. Okay? Is that clear? All right. So, all right. So we can look at the homework. Do you have any questions about the homework? Go ahead.
So on the first one, 3.33, it uses work equals m times a change in p over 1 minus gamma, and you haven't used that in class, I don't think, or at least not much. Is that like something?
Okay, so let's look at the problem. Is that okay? 333. So let's see what 333 is. Let's see what other equations are over here. Yeah, I don't see that. 333. Let's. Should I give you 333? Looks like a long number. This one here?
I don't think it's the right section.
I'm on the wrong section.
3.33. Probably.
Where am I here? What is chapter? Is this one? This is chapter 3.
Keep going down, like further down.
I mean, let me move this one so it's not that high. But I thought this is chapter 3 and 3.3 is this one, no?
Right there, right there, right there. Down, down.
Oh, okay. Those were questions. I get it. So as you can see, it's not that I've seen the problems before, no? I have no idea what they are. Okay, so here we are. So let's see, problem 333. Let's do it. Let's see if we can do this.
Probably put on
I do the other way around. I move this to the right, and I write to the left, no? Can you read, or do I try to make it a little bit bigger? Is that a little bit better? But now I need to move it to the right. How can I do that? This is not really responding to good. Okay, so I think that's a little more clear. So 333. Okay, so 2 kilograms of refrigerant 134A undergoes a polytropic process in a piston cylinder assembly. So as soon as you hear the term piston cylinder assembly, always do this type of figure. Okay, this is a bit automatic. I don't know if I need it, but I do this. So we know this is refrigerant 134A. The mass is 2 kilograms. Undergoes a polytropic process. So what is polytropic process? Is PV, I guess PV to the gamma equal to a constant, okay? Undergoes a polytropic process in a piston cylinder assembly from an initial state of saturated vapor. Okay, so we might not need this, okay, but you can do the figure or whatever you want. So let's say initially we are at saturated vapor over here. So P1 equals 2 bar. So maybe I did over here what diagram I'm doing here. Okay, I do the TV, so there should be lines of constant pressure. But then I go to a 12, so I don't know, maybe it's fine. All right, so we need saturated vapor. What else do we know? To a final state of 12 bars, so we know P2 equals 12 bars at T2 equal to 80 degrees Celsius. Determine the work for the process. We need to find work 1, 2 in kilojoules. So I don't see anything about the equation you are telling me over here. So it looks like you look at the solution
Yeah, and that's what I was saying.
and they give a magic equation.
Yeah.
Okay, that's, if you do that on the exam, really, really bad, okay? There is no magic equations with me. Okay, so let's see what happened over here. Okay, so let's try first to see what happened with, let's try to complete this, okay? Let's try to complete this figure. So let's say you have the tables with you. So you know the substance is refrigerant 134A. Okay, so what is the temperature T1? I don't know if we need it or not, but just by curiosity. So I guess we could come over here. What is the table for that? 810. Thank you. So page down. A6, A9, A10. So let's see, we know the pressure are 2 bars, so maybe 211, do you have A11? So I will go maybe to table A11, okay? So for 2 bars, what is the temperature? Minus 10.09, so minus 10.09.
With
Okay.
with the tables, if you had just decided to go to the first table, where it's the temperature table, and you had just
You can still
used
do it.
2.7, you would have a fraction of a difference in the final answer, but would you see that we use one table?
I mean, for example, you say to use this one, no?
Right, and if you went to 2.7.
So you can go here and interpolate. You see what I mean?
Yeah.
But that should give you very close. I don't know what
Right.
interpolation is.
Right. But you might still come out with, like, the answer might be close, but not.
Oh, you probably get, it might be the same with maybe a 1% difference or even less than that, okay? So you can still use this one, but it will be more work because you will have to interpolate between those two, okay? So I'm just trying to see over here, and we know P2 is 12, so here P2 is 12. And what is the temperature, the saturation temperature for P2? 46.62. And the temperature in our problem is what? 80. So what's going to be the state? Superheated. So we can do that if you want. If you do it here, obviously, it's not going to be to scale at all. But let's say this will be P2 equals to 12 bars. We know the saturation here temperature. What is it? 46.32. I mean, don't put T2, but we know T2 is somewhere over here, no? Where the saturation is 80, no? So really the process we are looking at is something like this. I mean, you should have done a figure bigger than that, okay? But again, it's... Okay, so we're probably gonna have to go back to the figures to find what is the value for the amps, not for the, sorry, for the specific volumes. But for now, let's just go and derive the equations. Okay, so over here, what do we know is the general definition for work. Minus P dV, no? Okay, where P will be equal to what? C divided over V gamma. So this will give us what? Oh, sorry. No, this is correct. Work 1, 2. Will be equal to what? Minus C dV over V to the gamma. But I already said that for you guys, is it easier if you write it under this form? Minus gamma dV. So what is the integral of x squared? X cubed over 3. So what will be the integral of this? I mean, you do the same thing, no? How did you do the integral of x squared? You added 1, no? And you divided by what? Yeah? So this gives you, let me go to the next page. I won't be able to do everything on that page anyway. So I'm here, and now I'm going to write this as what? As being equal to minus 1 over 1 minus gamma. I'm changing the order. And now what I do is that I'm putting the C inside. So it will be C V2 of minus gamma plus 1 minus C V1 minus gamma plus 1. Do you see what I've done between this step and this step? Okay, nothing too complicated. So now we know that this is a polytropic process. So polytropic process means that PV to the gamma equal to C, no? So for this one, I could say that C is equal to what? V2 to the gamma, and for this one, equal to what? V1 to the gamma. Okay? So now we have the expression that work 1, 2 equal to minus 1 over 1 minus gamma. And then what's going to happen to the V2 to the gamma times V2 to the minus gamma? They cancel each other, no? It's like having V2 divided by V2. They don't cancel each other, but it's equal to 1. So that will be equal to what then? P2 V2 minus P2 V1. Okay. Now, what else do we know? What is specific volume? Volume over mass, no? So that means that volume is what? Mass times specific volume. Okay? So I think probably the magic equation you are referring, which you see is nothing magic, is this one.
Yeah, and they used like a natural log equation to find gamma. Like it was natural log of P1 over P2 over the natural log of V2 over V1. And that's how they found gamma.
Oh, because they don't give you gamma.
Yeah.
Okay, I see how they find the P2, but basically I thought that was the equation you were referring to.
Yeah, it was that too. And then it was the two and a 5.
Okay, so let's do one thing at a time, okay? So let's say now we go and find what is V1 and what is V2. Okay? So let's say, so for V1, I think we're going to do the same thing. We need to go to table A11 at P equals 2 bar. You see, I'm looking here at the figure. So from that one, we're going to get that V1 is equal to what? Table A11 at 2 bar, which is this one. We know this is saturated gas, so we need to look at this one, no? At the VG. So it's equal to 0.0993, and this should be cubic meters per kilogram. Now V2 from the, what do we know about V2? From the figure we know that V2 is going to be superheated. So I'm guessing it's one more table, no? Table A12, is it a table A12? So we go to the superheated table. You see here they tell you to divide the value, so this is new, that's good. So superheated refrigerant So what do we know over here? We know the pressures and the temperatures. So let's see if we find pressure of 12. Okay, maybe it's on this one. I'm guessing 8, 10. Right hand side, that's what I thought. 12 over here. We need to look at what? At the temperature, so it's going to be difficult for me to look at this all at once. So it's 80, is this line, no?
Yeah.
So the one right above the orange on the first one. So it looks it's going to be this one here, no? And this one here, we're going to look, I guess, at this value here. Let's check, going up. This is the V. So what should be the V? So we go, let's say, to table A12 at P equals 12 bars and T equal 80 degrees Celsius. We have that V2 is equal to 0.02051 cubic meters per kilogram. Okay, so now for the gamma, okay, for the gamma, my first reflex, let me magnify this, will have been maybe to go to, let's see, some of these tables here, but they probably don't have it. Do they have this one for the, you see the gamma, they are for air, nitrogen, oxygen, but they don't have it for refrigerant, okay? So my first reaction would have been to come to this figure here and see if they had it, okay? You see the CP, CV, K. The K is what we have, okay. So let's see. Okay, so let me look at the solution and see what the way they do it. That way we don't turn around. So it's 333. Okay, so let's see. Okay, no, yeah, it's very simple. Yeah, I should have thought about that. It's not complicated. So basically what they do is this. So basically, you know it's a polytropic process. So polytropic process means that so now we're trying to find gamma. Polytropic process means what? P1, V1 to the gamma, will be equal to P2, V2 to the gamma. Okay? So over here, okay? So this will give us what? Let's say this will be equal to P1 over P2 will be equal to V2 over V1 to the gamma, no? Okay? So now what I'm guessing what they do is that they take the log on both sides. Yeah, so this will give you what? All right, and now my guess is that they use a property that log V2 over V1 to the gamma is actually equal to what?
Gamma log.
Correct. So you use the property that log let's say of AB to the C equals C log of A over B, no? Okay? So use that property. So basically, to the next line, we use the property log P1 over P2 equals gamma log V2 over V1. So that we can solve for gamma being equal to log P1 P2 divided by log, sorry for the V2 V1. Okay, I'll go to the next page. Okay, so now in this problem, what is V1 and V2? Yeah? Okay. So I guess now you can just go and substitute, no? And then you come back to this equation over here on top, the one for work 1, 2, and you substitute. Yep. Okay, so since I'll let you do the numerical application. But you see, there is no magic equation, no? Okay? Yes?
When we start doing the numerical calculations, do we need to convert everything into kilopascals?
For this problem? Oh, that's a good question. So, once you start doing the calculations, yes. Once you come here, you need to transform the bars into kilopascals to get the answers in kilojoules. Yes. All right? Yeah, remember, if you write down the units, that would be the best way to check your answer. Okay? Yes, because if you use bars over here, it's not going to be the same, no? You need to transform the bars into kilopascals first.
Is that the same thing for finding gamma? You can put them into the pascal?
Yes, same thing for gamma. I mean, gamma will work because you get the same. The ratio will be the same, no? Will be twice. You don't have to, but to be safer, I will always transform everything, okay? If you want me to give a general rule. But in this case, no, because the ratio will be the same. Okay? But what about V2 and V1? No, V2, V1, you can also leave them as they are. The ratio should be the same. So for example, here for V2, V1, I don't think you need to use this. You can use the ratio V2 over V1, no? You see the specific volume V2 over V1 because anyway the mass will cancel, no? Yeah? So the ratio will be the same. Okay, so more questions about the homework? Yes?
356 part A.
There is no part A or B unless it's something very clear. Is so 356, let's see what 356 is. All right, so all right, here's the problem. 3 56 Okay? Let's see if I can move this to the right over here. All right, I tried to write over here. So let's see, 356. So again, a piston cylinder assembly. I mean, it's pretty monotonous, no? Always the same figures. Piston cylinder assembly containing water. So let me just say H2O, okay? Containing water, initially at liquid at 50 degrees. So let me just say initially 1 liquid at 50 degrees Fahrenheit undergoes a process at constant pressure. Okay, we know that because whatever happened with piston generally is constant pressure, no? Okay? At constant pressure of, so P constant equal to 20 lbf in inch squared to a final state where the water is vapor. Okay, so state 2, I should have done the figure, but vapor at T2 equal to 300 degrees Fahrenheit. Kinetic and potential energy can be neglected. Determine the work and heat transfer in BTU per pound for each of the 3 parts of the overall process. What are the 3 parts? Okay, so let me, I don't know what the 3 parts are, but I guess we're gonna find out. Oh, I think I know, but let's see. So basically, let's do a figure. So I guess here the easiest one will be, again, the TV, no? So we have constant pressure, which is 20 lbf in square. So let me not guess. I cannot kind of guess what's going to happen, but let's say T2. Wait, I don't want to guess, okay? Because I think I know what's going to happen, but okay. So we are in water. We know P1 equals to 20, no? So to what table we need to go? Maybe you can help me here. Should be A2E, something like that, or A3E. So let me do this a little bit bigger, okay? Down. What is going down? I want to go. Oh, I want to go up. So I guess it's going to be A3E, the one I want to look at. Which one is this one? This is the one for the pressure. So table A3E at what? At 20, no? Okay, so for this one, what is the saturation temperature for 20? So 227, so Johnny will have over here 227. Okay, I think what's the problem? All right. So basically T saturation is over here, no? 227. However, what do we know is that 0.1, let's say it's going to be here at 1. Where T1 is going to be 50. Okay? So since T2 is higher than T saturation, where is going to be the state 2? So it's over here. So now, so that's what I thought, but basically what would be the three parts then? Would be between 1, so that the water becomes what? Saturated liquid, no? How do you want to call this point? Let's call it L for liquid. Then you go here to saturated gas, G, no? And then you go from this one to this one. Okay, so let's see. So what do we need to solve in this problem for? Oh, the work and the heat transfer. Okay, so let's do first the work. So for the work, again, the general equation for the work is minus P dV, no? So in this case, what we do, P is constant. So the work will be equal to what? Minus P V final minus V initial. Okay? Or using the specific volume, we're going to have the general expression for the work is going to be equal to minus MP V final minus V initial. Oh, the one is BTU per pound, so what do they give you then? Ah, no, they don't give you the mass over here, no? So yeah, I have the impression they give you the mass. So forget about it, it's completely the other way around. So you go from here using this, we have this. Okay, you move it to the other side. Yeah? I don't know why I had the impression we had the mass. I was still thinking about those two. You see, and that's because I did not write over here what we needed to do. So we need to find work over M and Q over M. Is that what we need to find? For each one of the three processes? Okay? You see, I don't write it down, then I do the mistake. That's why I say this part is very important. Okay, the setup of the problem. All right, so let's do the first one. So let's go from point 1 to point L, okay? So from 1 to L. Ah, I see why you asked me this problem. Yeah, this can be tricky here. Let's see what can be the problem. All right, so over here, we know that the expression for the work is going to be what? Work 1L over M is going to be equal to minus P VL minus V1. Okay? So in order to find VL, that's the easy one. And let's say V1. So let's see. How did you find V1 and VL? You can find VL. How did you find VL? So you went to the what table A2, no? No, A3. Is that what you did? I know I'm asking, so A3, but this is at 227. Okay, so 227. So VL will be the V fluid over here, no? Yeah? At what pressure? 20. So we are over here, is that correct? So we go to table. What is this table? A3 or A3E. At P equals 20, you find that the L equal to 0.01683. Okay? So basically what we did is that on this figure over here, we found VL. Now we need to find V1. So, all right. So there is nothing perfect, okay? So, but generally what people do in order to find V1, because once you go to the tables, they don't give you tables for super liquid, for super liquid products, no? You have tables for superheated, where they give you the pressure in function of the temperature, okay? But they don't give you the equivalent for the liquid, okay? So the way to do that, and there's a reason why they do it, is because the properties, once they stay in the liquid state, they are basically constant. So what you need to do on this one is that, what is the other thing that you know about state 1? You know the pressure, and what else you know? The temperature. So now you can go to what? Table A to E at 50 degrees Fahrenheit. Okay? And this time you will look at what? The V fluid at 50 degrees Fahrenheit is 0.01602. Okay, it's an approximation, it's nothing perfect, okay? But what do you think that's the approximation they are doing? No, because what is the pressure over here? It's 0.17, it's not 20, it's point.
That's the inverse of density.
What is the inverse of density?
0.01602. The density of water.
Okay, so that's good. So basically, yeah, so very good point, okay? What I was gonna say is that, do you remember what we say is that once a substance stays in one state, the properties do not change a lot, no? If you look over here, do they change a lot, the properties? Okay, so specific volume, like he mentioned, is the inverse of the density, no? So do you think the density of the water is gonna change a lot when it is in liquid state? Okay, so basically the assumption they are doing is that the properties do not change a lot once you know the state in which they are. Okay? So then V1 over here should be equal to what? You see, it doesn't even change over here, so 0.01602. So from table A to E, so table A to E at T equal 50, you find that V1 equal to 0.01602. Okay, so I'll let you do the numerical application for okay, be careful over here because you're gonna have the results in pound force per feet, and then you need to use the transformation pound part force per feet to BTUs, no? the 778.17, I think it is, all right, to go to the BTUs, okay? So you do the regular application. Now we go from L to G. What would be the work? Would be work LG over M will be equal to minus P VG minus VL. I think now you all know how to do this. From where do we get the VG? Table A3E at P equals 20, no? We can get the VG. So let's see, let's go to table A3E, or yeah, A2E. So A3E at 20. We need to look for what? For the VG, no? Which is 20.09. Okay, from this one you can calculate the work LG over M equal to minus P VG minus VL. And finally, what do we need to do between G and 2, okay? Even though you might not see it, I always have the figure over here, okay? V2. So now we need to go to what type of tables? So let me write down work G2 over M equal to minus P V2 minus VG. We need to find V2. What is the state of 2? Superheated, no? So we go to the superheated tables at 20 and what is T2? 300? Yeah. See, I added over here 300. So superheated tables at 20. Oops, I think I skip it. 20. They don't have the they have the 300. So the V, I'm guessing, is the first column. Yeah. So the second column after the temperature. So what do you get for V? 22.36. So table A4E at P equals 20 and T equals 300. That gives you V2 equals to 22.36. Oh, okay. I'm just thinking that now for the Q's we need to do the same thing for the U's all over again. So. Yes.
You can do the rest of the U, but it's the U for U1.
You do the same thing. You take the U1 for a saturated liquid for the temperature of 50.
Even if the pressure's not the same?
Even what?
Even if the pressure's not the same?
Yes, because you're still following the same assumption than before. Is because the same thing as the density you mentioned is the inverse of the specific volume remains constant. The internal energy is also a property. So we can see, is it a big change depending on the temperature? It should not be a big change, no?
It does change a lot.
It does change a lot.
Like at 32 degrees Fahrenheit, UF is like -0.01, and then 50 degrees Fahrenheit,
Well, let me look at it, okay? Let's see what happened over here. Okay, so anyway, let's finish this one. So you do this, okay? All right, and then I'm going probably to make this a lot shorter. So we have this 67, 67. So you calculate all those works. And now let's say for internal energy, so 68 for, sorry, not for internal energy, for Q. Okay, what's happening is that we do the first principle of thermodynamics. Which means what? Q plus work equal to change in internal energy. Okay? Or which means Q over M plus work over M equal to the, instead of the capital U is the lowercase u. So you get Q over M equal to, let's say, U final minus U initial minus work over M. Okay, so let's see if we can make a table. I don't know if this is going to be good or bad, but let's try it. So points, let's say it will be 1, L, G, and 2. Table, what we need to look at. And here we put U, okay? Let's see, that will make it a bit faster. So maybe let's start by the end. So we don't have any question because I think the problems are going to be once we get to 1, no? Okay? So let's see, by the time we get to 1, we can think about something. So for 2, I think we need to go to table what? A for E, no? Yeah? At P equals 20. And T equals 300. What do we have? Hopefully I haven't moved the table, so it's P12, 22, so I guess it's this value here, no? So what it is? Yeah, U is 1108.7. Okay? For G, we can probably go to table, we could probably do it for table A for E, but let's say we do it from table A3E, and let's do at the same time L and G, no? Table A3E at what? P equal 20. Why is it going down? Up. So A3E at 20. Let's see if I can make it from here. At 20, we know V fluid and V gas, no? So that means that V gas is equal to 20.09. Oops. No, that was the other one. Sorry. 196.19. was looking at the V. So it's 196.19, this two over here. Okay, I did the wrong one. All right. Okay, so anyway, V liquid is 196.19, and the V gas is 1082.0. Okay, UF and UG, no? So I put over here, sorry for that, it's 1082.0 over here. It's not going to be clear, so let me write over here. 182.
So for the values for V earlier, if we knew that we were going to find V for all these different steps,
Yeah, you could have done it
could
at
we
the
just
same
do
time.
this little like table first?
Yeah, yeah. It would have been a lot smarter. But I'm not that smart, okay? Yeah, it would have been a lot smarter to do the table and put the values for U and V. Okay?
If you knew, you
Yeah,
would
but-
know that
Yeah, I was just trying, to be methodical, but being methodical and go through the procedure is not always the most optimal way to solve the problem. Okay? So now, for one, I think the only option we have is to go to table A to E at T equal 50, and let's see if that's a good assumption or bad assumption. I mean, if somebody, for what you say, is a bad assumption, no? So table A to E at, is it 20 or 50?
50.
Yeah, I mean, what can I say? It's not a great assumption.
Use Q equals MC dot T. That formula. Q is the mass times feet of water, which is the temperature. We don't know the mass, but we're finding Q over M. So Q over M is
What is the way you want to do it? Say that again.
Q equals MC delta T, where M is
You say, but you say the C sub.
C is the specific heat of water.
Okay, but I agree with you. But you end up with the same problem with the specific. So specific.
You know, it's on the unit sheet, specific heat of water,
Yeah, I know what you're saying. So what you want to do?
and then delta T would be 227.96 minus the 50. That would give us Q over M, which we're trying to find.
Yeah, but where did you find the CP from? From one of the tables?
No, this is water. C is the specific heat of water.
Yeah, but you see, you're making an assumption there. You're assuming that the C of the specific water is constant. The C of the specific water, if you want to be accurate, it will also change with the temperature, because what is the definition of C? It's partial of U with respect to T at a constant pressure. You see what I mean? So you end up with the same problem, because really you will have to find a table that gives you the value of C for the different temperature. Do you see what happened? So no matter what is an assumption, so here you see why maybe here is not a good assumption, because what's happening? This is not that constant, no? Yeah? But I mean, the only way I see to do is this way. So U fluid over here will be 18.06. All right, but if you want, I'm gonna do this. So this is the way I would do this problem, okay? What did they do for this one on the solution manual? Do you know? What was this problem? 3.56. So they are smarter than me, they do the table. But basically they do the same thing for the internal energy, no? You see? But what's important over here is not that much that you look and say, okay, I got it right. But now that you realize that, okay, that's the way we solve the problem, but you need to be aware that this is not such a good assumption, no? Because properties here of internal energy do not remain that constant in function of the temperature. The V's remain pretty constant, no? as you can see on this column. But the U's do not remain that constant. So the proper way to do this will be we will need a table where they will give you the properties of super saturated liquid of water, no? Yeah? Okay? But it's not the case. So it's almost 12:30, so I think that's about it for the problems. Okay? So for the exam, I mean, guys, sometimes I used to do it a lot, now I do it less because some people told me that some people were kind of cheating, bringing solutions. So, but I used to give a lot of problems from the homework on the exams. It can still happen, but it might not happen. But I always try to find something that would be similar to something we have seen together, no? So like I mentioned to you, first problem, something about the first law. What happened with the power cycle, refrigeration cycle, or heat pump cycle, no? Okay? Second problem, something about heat transfer. Conduction, convection, or radiation. Okay? Third problem, something about the problems we did today, that you need to use the tables. Any question about the exam? Yes?
Is it going to be an hour 15 or is it going to be 50 minutes?
No, I give you the hour 15. I mean, no, it's useless that then we do something different. I'll give you the hour 15, okay?
Should it take that long though? Like theoretically, if you know what you're doing,
No.
it should take 50 minutes, hours.
Yeah, probably, yeah.
Like 15 minutes time.